Okay, so, yeah, we'll start now. The lecture today is about many objects and distributions. And so it's moving on the single object and the more complicated analysis of the single objects to looking at many different objects at the same time and how you sort of analyze the distributions you get there and what sort of um, further results you can get out. So that's an example, of course, of the weird formatting. That won't be in the final version, but currently it's in there. And all the slides are scrollable now. So instead of having two columns, you can just scroll up and down through them, which should make it easier. And then you have in the bottom left this contents, where you can then see what all of the slides are and jump to a specific slide, which should make it easier to find things in the lecture. So in terms of the outline, what we have, the course outline is the same as it was before. This is sort of the last lecture where you'll actually be learning new techniques until sort of the guest lectures at the end. And the idea is that once you've covered all of these techniques, that we'll then try to apply them to more complicated data sets and not just synthetic data sets to solve real problems. Because up until now, it's just kind of developing the tool set out so that you're familiar with what kind of analyses are standard and available. And then it will be kind of how do you apply these tools to more complicated systems to solve real problems. Cool. The literature for this remains more or less the same. There's some other ones I've added which are visualizing for processing of tensor fields. And so if you're not as familiar with tensors and this aspect is interesting for you, I'd recommend looking at that in more detail because we just go over it very briefly. Voronoi tessellations are also a pretty important aspect in this, and we cover them in a very applied way, but you can go into much more detail, and particularly for material science-oriented people, there's a lot of aspects that are very interesting for that when you're looking at glasses or sort of these quasi-random structures that you can start to quantify them with tools like Voronoi analysis, and they're used in all sorts of other fields. So feel free to look through any of these articles. Then for alignment and distribution, there's two papers that cover that fairly well. It's applied to foam and other sorts of analyses. And so you can see how this tensor can be used to actually quantify strain in materials where you don't know what the strain is beforehand by looking at actually how the distribution changes before and after. And then finally, two-point correlation, which we just cover briefly at the end, is very helpful in a lot of material science applications, and it's very frequently used to quantify random sort of heterogeneous materials because you don't have a lot of tools available for looking at them. So when you have huge structures that are just sort of a messy mixture of several different components, two-point correlation can give you some sense out of this and help you see structures that aren't immediately apparent. And that's actually what some of the exercises will go over, because there we'll take sort of random structures where your eyes very quickly see that there's sort of a layer structure, for example, and what kind of tools or what sort of analysis can you use to quantify that structure, because if you count points or just look or measure the distance between them, that won't give you the structure you're looking for. And so what tools can help you take huge amounts of data and start turning them into useful metrics? So previously, we've covered sort of the image enhancement, the automated segmentation, component labeling, single shape analysis, and then complicated shapes. And so basically, we've created a bunch of input data that we want to analyze in more detail. And so if you think about sort of cellular imaging, usually you're not taking an image of one cell at a time. Usually you're looking in sort of pathology where you have thousands of cells on a slide, and you've analyzed now each of those cells, and now you need to do something with that overall statistic. And so how do you classify sort of how they're grouped together and everything else? And that's what we cover sort of in this lecture. And so The motivation is really looking at kind of local environment. So how closely are the cells spaced together? How many kind of neighbors do the cells have? What is the Voronoi tessellation, and how does this help us understand these structures? How does this then map to kind of distribution, and how can we quantify that? And then the global environment. And so global environment is sort of looking at the entire object, and how do we quantify things like alignment? So this is sort of the idea we covered in the very first lecture, where we said that you have different structures, and kind of the typical way of categorizing them is that you say this one, all of the filaments are very well aligned, and in this one they're very poorly aligned. But this is a really vague metric, and if you want to be able to quantify it and put a number on it, then you need to have some way of assessing this better. Self-avoidance. So this can be very helpful in understanding how sort of structures grow or spread. That, are they randomly placed, or is there some sort of pattern that they're being placed with, and are they avoiding each other, or are they clustering together? And then finally, this two-point correlation function. So we examine sort of a bunch of different metrics, and kind of what we have is two general categories of metrics. So we talked about sort of the local and the global, and we have point and voxel-based operations. And so the point operations are where you look at each object or each segmented component that you have out, and you treat it as a single point. And this point is then usually at the center of volume or the center of mass, but you sort of collapse all of your objects into a list of points. And so these point operations are things like nearest neighbor, Delaunay Triangulation, distribution tensor, point-based Voronoi tessellation, and alignment. And so this is, looking at your analysis as sort of a list of points in X, Y, and Z. And you have, sort of a list that you then want to quantify something going on in this list. The other operations we have are the voxel-based operations. And so this is where you do have separate objects, but you want to look at the voxel information and not just the point information. And so Voronoi tessellation can be done in a point-based manner. It can also be done in a voxel-based manner. And so hopefully the difference between those two is sort of clear at the end. Neighbor counting is where you look at the number of different neighbors a given object has. And so if you want to look at what the objects are physically in contact with, then you can't simply look at the center of mass. You need to look at the actual voxels and see which voxels are actually touching. So sort of similar to this component labeling approach, where you have to go through and see, are they actually in contact, or how far away are they? And then this two or endpoint correlation functions require all of the voxel data to do correctly. So if we sort of look at what we start with, we've been able to get rid of the noise of the image and kind of find the cells. If we take the cell image as the example, we've analyzed the shape of the cells using sort of the shape tensor, and we've separated cells that were sort of joined together using watershed, which is one of the techniques we covered last week. And now we kind of want to, we can characterize easily the sample by looking at average and standard deviation of the metrics that we've extracted. So if you take all the volumes of all the cells, you can calculate the average very simply. You can calculate the average orientation, the average surface area, the average sort of length or anisotropy, or any number of these other metrics. But that sort of doesn't tell you that much about the cells. And so if we go back to this image before, you're looking at sort of all of these different cells, and actually the volume, there are some fluctuations with volume. It might be an interesting parameter, but if you're trying to figure out how many cells are alive, if small cells are dead and large cells are alive, then you'd want to look at the volume distribution, and you could simply label it. But if the cells are not so simple, so if it's not just small and large, maybe the living cells are round and the dead cells are spiky and pointy, which is many times the case. And for that, you could look at sort of anisotropy or circleness, where you sort of define that you fit this ellipse to it, and you compare the shape of the ellipse to the shape of the object. And if it's very spiky and pointy, then there'll be a very large mismatch between these two. And probably the most common analysis that we have then here is that you'll find cells are alive or dead based on sort of how densely packed they are together. And so looking for regions where they're very close together would be indications that they're alive, and sort of single cells that are really far away from all the other cells are probably dead. And so the tools that we've developed thus far aren't really helpful in solving this problem. And so, we can examine the raw positions, but that doesn't really help us. You can kind of make boxes arbitrarily and count the cells inside of each box and say this region sort of has very few cells and this region has large cells, but that's fairly arbitrary. How do you define the box as well? And how do you do this then for lots and lots of samples? And if you're trying to compare two regions within a sample, sort of how do you design those regions well, or how do you compare these cells to these cells in sort of an easy manner? And then you want to be able to do, because when you get slides like this, you typically get hundreds or thousands of them. How can you scale this up to do this on a lot of different samples? Cool. I don't know why that image shows up twice. Anyways. Cool. So if we wanted to kind of ask different questions, if you wanted to know how the cells are communicating, or sort of what's the network of cells that we have, if the cells are physically touching, then this is where sort of the watershed technique is very helpful, because then you can take the cells that are touching and separate them into kind of the different body cells that are linked together. Maybe cells that are oriented in the same direction are communicating. So this is quite frequent in bone, that the orientations of the cells are sort of aligned with cells that are in contact or communicating with each other. And so then you can look at this different orientation and try to figure out, if they're very close, then they're probably communicating. If they're very far away, then they probably aren't communicating. The problem we have for this is that orientation is an angle, between 0 and 360, and averaging doesn't work very well. So if you have 0, and that's vertical, and 359, and that's slightly 1 degree off of vertical, and you average them together, then you get 180, which is then this. And this is in 2D. In 3D, you then have two angles that describe each cell, and so how can you combine them together in a meaningful way? And this is kind of where orientation gets very challenging, because it's not very easy to quantify using standard tools, and it's very easy to make mistakes. So maybe cells that are close enough are communicating, and so how do you define close enough? Is it a certain distance that sort of, maybe a given molecule can diffuse, and that sort of indicates that they're communicating? Or is it sort of there's no other cell between them, and that means that they must be communicating? How do you define things like this? And then maybe cells form kind of hub and spoke networks, and how can you start to extract these networks and figure out which cells are sort of more important and which cells are less important? So, if this cell is really far away, it's probably only connected to this one, and this one is connected to 4 or 5 different cells potentially, and so this one is probably more important in this hierarchy. Of course, for imaging of neurons, this is very important, because you want to be able to identify sort of where the action potentials are firing and how this network is linked together. And so if you can understand that the signal is propagating from here to here to here to here, you can start to do better experiments on the network and understand what's going on. If you want to know how the cells are sort of nourished, which cells are being sort of well supplied with nutrients and which cells are not. If you want to understand sort of looking at how closely packed they are together. You can count cells in a box, but that's not always, reliable. How do you define the box? Isn't clear. And maybe cells that are oriented around canals, which supply them, are well nourished. And, first of all, how can you kind of link these two pieces of information? And how can you measure these kind of distances easily? And so we covered the distance map last time. And so that would give you the distance from the canals if you made a distance map. And so you could then sort of overlay those two pieces of information. But if you wanted to figure out if they're oriented around the canals, then you have another challenge. And so how can you try to solve that? And so the tools that we sort of need, or that we need to solve sort of the problems that I mentioned, are a way for counting cells in a region and estimating a density without sort of defining boxes or creating arbitrary definitions beforehand. And so how can we define something like density in a way that's very reproducible, in a way that other people can apply, and you can apply to a large variety of different images, where it's really not too specific for the exact setup that you're analyzing. The second is kind of how do we find out how many objects are near a given object? This is typically called nearest neighbors. And so what is the sort of standard way of doing that, and how can this information be interpreted? The third one is sort of how far apart cells are and comparing different regions within the samples. And so are cells really closely packed together, or are they really far or spread apart? And is there an easy way to measure that? Finally, the way for quantifying and comparing orientations. And so how do we look at thousands of different objects with different orientations and come up with some understanding of, are they aligned? And which groups of objects are oriented very well together, and which ones are sort of oriented in different directions. And what would be great is if there would be sort of tools that we could use that were kind of not too specific for one kind of problem. And so what we've seen, that for example, with all the segmentation tools we developed, they work really well on two-phase systems. So where you have bone and air, or you have cell and background, or sort of any number of these other combinations. But when you have three phases, most of these tools stop working well. You sort of have a lot of other issues that you need to take into account, and you can't use the sort of fully automated methods anymore, or you have to always treat them as two-phase systems. And so what would be cool is if we could develop tools here that would be applicable to 3 or 4 or 5-phase systems, so that you don't have to throw away all of the sort of knowledge and developments you've made every time you add a new phase to your system. One of the important things here, and so depending on what kind of technique you use, this can be pretty crucial, is this idea of kind of destructive measurement. And so if you're working in sort of in vivo imaging, then maybe this isn't as much of a problem, where you can actually look inside of a patient or an animal and measure something and then come back and measure it again. But in most experimental setups that you have, so pathology, high resolution X-ray imaging, electron microscopy, any methods where you're slicing things up, your sample's destroyed. And so when you take one measurement or one time point, you can't easily take another time point because the sample is gone. You can't measure the same thing that you measured before. And even with techniques like X-ray tomography, which allows you to measure the same sample multiple times, you can have an effect on this sample. So in hospitals, because the resolution and the dose is low enough, this effect is very minimal. But if you look at techniques like synchrotron X-ray imaging, the dose is much higher. And so if you measure a sample like bone, what we've seen is that all of the collagen in the bone is destroyed by the X-ray. And so if you're trying to measure a before and after, you give a sample a treatment and you want to see how the structure evolves, then you actually don't have bone anymore. You have calcified tissue with damaged collagen inside. And the mechanical properties of this are very different than the mechanical properties of normal bone. And so if you're trying to compare before and after, you can't do that very easily. And so what you need to do is you need to take a bunch of samples before treatment, measure them, and then a bunch of samples after treatment that have never been measured before, and measure them, and figure out some way to compare these different groups. And so you can't really match up any information from the samples before to the samples afterwards. You have to look at the statistics and see how they shift. And so, you have a very unique set of problems with these type of measurements, because you're trying to kind of show changes and you don't necessarily know the variability of the underlying samples, because you're not looking at the same thing, you're looking at very different things. And so particularly for understanding how these distributions or how these other results change, having tools that quantify the analysis you do or collapse the analysis you do down to a single number make this much easier. So what's important about this is what we want to be able to find is sort of metrics and results that tell us something meaningful about the sample that allow it to be compared to other samples that aren't necessarily the same. And so if you're looking at a single cell and you see that a single cell before and after, grew by a factor of 2, that's very easy to say. But if you have a whole collection of cells, you want to be able to show that on average this is what happened to the cell. And sort of, sample B after treatment looks like sample A stretched to be 2 times larger. And this is where you can't map everything in B directly to A, but you can quantify B in a way that you can then compare it to A and say that there's a stretch or there's 2 times larger. And I think this will be clear with some of the next examples that make this more concrete. Or the volume fraction at the center is higher than at the edges, but the organization remains the same. So how can you quantify things like organization independent of things like volume fraction? So what we have is that we take sort of a smaller region of the sample where we have all of these different points that we're looking at. And so basically this is the region we're looking at, and this is the list of cells that we have. And so each X and Y represents the center of volume, or center of area. And the Vx and Vy are sort of the unit vectors showing which way that cell is oriented. And so this is what we got from kind of the principal component for shape tensor analysis that we applied to this data earlier. And so we can take this, and this is kind of the standard analysis we can get. We can then do the sort of distribution of all of these different metrics to get the minimum, the median, the mean, the maximum, and sort of these quartiles for all of the different values that we have. And so this sort of quantifies it, but it isn't really that helpful. And so particularly with something like theta, which is this angle that we calculate, a mean or standard deviation of theta doesn't tell us very much. And so, if you have 359 and 1, you have a huge standard deviation and you have a mean of 180. And so it doesn't match anything with your sample at all. And so we see that kind of that simple statistics doesn't give us the result that we have. This minus 180 and 179 is 359 degrees apart, but in reality, they're only 1 degree apart. So there's many different examples and angles where this becomes a major problem.
Would it be enough to just change the angle system from 0 to 180? It sounds so simple, but would that work? Instead of using a 360 system, use another system where your 0 is up and then do it to 180 and then you go back down from 180 to 0. Maybe you have plus and minus, then you can look at absolute mean of the absolute values.
Right. So if you have 0,
either,
right. So if you have 0 to 180, then minus 180 and 179 are this. So they're different by 1 degree. So you can choose a point. So if you know that most of your samples are between like minus 15 and 15 degrees, and you choose 0 as sort of your center, then it's very unlikely that you'll have something at minus 180 and 179.
Mm.
But as soon as you have a single one there, you always have this discontinuity. And so how can you get rid of this discontinuity? Because that's quite important. And there are really nice tools for doing that. And so it's not like an unsolvable problem. It's just unsolvable if you try to keep it as a single number, because that doesn't describe it very well. And then you have the problem that in 3D, you then have two angles. And so then you'd have to solve that for two different angles, and you'd have to be able to visualize your problem well to make sure you're not making any mistakes there. Yeah, and so this was an example of sort of, the mean distribution for that. It's not very interesting in this graph. The other aspect is sort of density. And so density can be quite easy to calculate if you sort of take the simple approach where you basically count how many objects are in a given region or volume. And so if you have here, this is 3 simple objects that you can then see. This is 10, this is 100, this is 1,000. And so this gives you kind of the result that you would expect. Density matches what you see visually very well. But now we have 4 different groups that all have exactly the same density. But they look completely different. And so we see for this that density actually doesn't help us very much in describing the groups. For this one, all of the samples are packed here. But since the box we chose is from 0 to 1, then they have exactly the same number of objects because the box is too big. Same thing with this one, or not quite the same thing, that it's much more closely packed here, and it's much less closely packed there. And so the box doesn't really fit very well to the object we're measuring. And so here we kind of see that density doesn't help with analyzing these kind of objects because all of these have exactly the same density inside of them. For sort of neighborhood analysis, the simplest one that we have is sort of this nearest neighbor idea. This is also very frequently used in sort of machine learning and other topics, and so it's a good concept to be familiar with. And that's basically if you have a given set of objects with sort of the centroids at x0, x1, x all the way to xn, that the nearest neighbor distance is the distance to the closest point in the set, or so from a given point, it's the distance to the closest point in the set that's not the same point. Because of course, if it were the same point, then it would be 0. And so this requires having a distance metric that defines the distance between 2 arbitrary points in your system. And then you can perform this analysis. And basically what you get is you get a nearest neighbor distance, which is this distance itself. And you can get a nearest neighbor angle, which tells you the angle to the neighbor that it's closest to. And so this can be very helpful for knowing, for seeing some basic patterns that are present in the system and sort of describing your sample well. If you have a simple system like a grid, this can be problematic. And can you think of why this might be an issue if you have a grid?
Because if one point is out of box, it's actually close to the point in the next box, then you can see like across the box.
Across the box.
So if you split your picture in small boxes,
Uh-huh.
then you cannot see across the box
Yeah.
from one box to another.
Right. So that's the problem with using boxes. But for the nearest neighbors, we don't need boxes at all. So sorry, the grid, what I meant with the grid is that if you have sort of if you have a point at 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, why might nearest neighbor be a difficult tool to use there? So if you imagine a space and there's just points evenly distributed in x and y.
Because they're equidistant. So
Exactly, yeah. So that you have points that have 5 neighbors or 4 neighbors that are exactly the same distance apart. And so how do you pick which neighbor it's actually closest to? And particularly for something like the angle, if you're trying to see something about the organization of the structure, then the angle is kind of arbitrary. It's whatever point it happens to think it's closest to, and if you make a small, tiny deviation, then it will choose one point over another point, and that's not necessarily so meaningful. If there's points that are spread out kind of randomly, the nearest neighbor distance works really well, because the distance to the first neighbor is much less than the distance to the second and the third and the fourth. But if you're in a perfect grid, then the distance to the first is exactly the same as the distance to the second, to the third, to the fourth. And so this minimum function isn't very smooth anymore. So that's typically described. And so in 2D, this is then 4 equidistant neighbors. In 3D, this is then 6. This tends not to be a problem for real data sets. It tends to be more of a problem for simulated data sets. But it's very easy to run into, because when you're simulating data, it's easy to just have a grid. And then when you try to do something like nearest neighbor, then you have randomly selected angles. And when you're trying to calculate the distribution, it can be not very meaningful. And so here we can see the nearest neighborhood analysis for this grid. And you see this nearest neighbor vector is completely arbitrary. And so it's not any closer to this point than it is to this point, but it just happened to pick that arrow as being the nearest object to it. And so this is where you kind of have that problem that this angle doesn't really mean anything anymore, and this nearest neighbors vector can't be used. And so what we'll do is show kind of in silico systems that apply a fixed deformation to them, and then we quantify them with these tools. And so basically what we'll have is we'll have a sample where we try to compress it, and the compression we apply is very simple. You take the original coordinate system and you multiply it by an alpha, and if it's less than 1, it's compressed. If it's greater than 1, it's expanded. Shearing, where we have sort of this transform matrix, where x is x plus alpha times y, and y is simply y, and that sort of just shears the sample. Stretching, so this is a slightly weirder transform. Basically what this does is this moves the points closer together in the center and makes them further apart in the edge. And so if we look, there's no example there. If we look at this point, this is sort of an example of this stretching, that the samples are packed much closer together towards the center and much further apart towards the edges. And so you have very dense samples here and much less dense samples there. The last one that we have is sort of swirl, and this is to have one transform that's really kind of nonlinear and does something very unusual with the data, where the data sort of just get twisted, but they don't get uniformly twisted. The angle that they get twisted out sort of increases as you get further away from the center. So if you had a 0, or not a 0 here, if you had a 0 here, then it wouldn't be twisted at all. And the higher this alpha is, the higher the sort of twisting or swirling that you have in your system is. And the idea with this is that we can then take a system like this uniform grid of points, and we can apply these transformations to it. So this is the system in sort of its normal state. This is a system at 0.8, and this is a system at 1.2 of this compression. And so this makes it smaller, this makes it bigger. And the idea is that we can then see very easily what happens to the metrics that we create when we apply these transformations. Because the problem that we have is when you use tools like nearest neighbor distance on a biological sample or a materials sample, it's very difficult to interpret the metrics or what they mean. And what we want to do here is show how they look on fully synthetic systems to get a better feeling for what the metrics means and how can they be interpreted on real samples. And so here, compression, I mean, you could probably have visualized without this graphic. If we then look at sort of the nearest neighbor orientation, that with 0.8, how do we expect actually the nearest neighbor to change when we apply compression?
The distance to the nearest neighbor, or
Yeah.
the distance gets smaller.
And linearly or?
It's the compression is more. The compression is overall.
Right.
So it should
I mean, the compression is exactly,
same for any point. For any
It's
area
exactly
of
that.
image.
Yeah.
And the overall, the distance should go down. But then the question is, which one is the nearest neighbor will change, or
right.
it'll still be 4, which are nearest neighbors.
Yeah. So the distance goes down by exactly that factor. So when you apply this transform, the nearest neighbors stay the same. The orientations of the nearest neighbors don't change at all. The only thing that changes is that distance. And so when you compress it to 0.8, the nearest neighbor distance goes down by 0.8. When you stretch it to 1.2, the nearest neighbor distance is multiplied by 1.2.
How do you use this fact that's gone down? What is the advantage of having? I guess you'll get to that.
Right. Well, the idea is that what we're doing is we're applying a transform that we understand to a system,
Okay.
and then we want to see how the values
Oh, I see.
of these metrics change. So if you have a system and you're looking at sort of a bone sample, for example, and you compress it, and before you compressed it, the nearest neighbor distance was 10 microns.
You do the calculation of nearest neighbor before and after the transformation.
Yeah.
And then that helps out.
And then you can try to understand what transformation actually happened. Because usually you can't, I mean, in most systems that you're looking at, you don't actually know what happened to your system. You simply know what happened, what it looks like before and what it looks like afterwards.
So the transformation is a physical transformation? That's
Not
being
always.
done on a sample, or it's just mathematical? So you have
This
a-
is all
This is
mathematical.
mathematical, but if you know what transformation you yourself are applying, then you know what to expect.
No,
Okay.
because when you compress a bone sample, you don't actually know what happens inside.
You compress it mathematically. You have the data and you compress it.
Right. But we don't do this because that's not interesting.
Okay, what do you
You take a bone sample and you actually compress it. You actually put it in a machine and you smash it. And then you want to figure out what happened.
Alright.
And so then you can look at tools like nearest neighbor distance to figure out what actually happened.
Wow.
And so what happens, in many other systems, you're not actually applying the transformation. That if you have a patient and you give them some hormone treatment and you have before and after, how can you compare what happened? And so if the hormone treatment did a compression, then you'd expect there to be no differences in the nearest neighbor angle, but the nearest neighbor distance to be scaled by a factor. And so if you saw that the nearest neighbor distance was scaled by a factor, you could then say the effect of this treatment was compression. And so the idea for this is that you can then sort of back calculate what must have happened between step A and step B.
Makes more sense.
Yeah. No, it's a little bit unclear. Here, I can.
It was just unclear where you're getting at. So it's getting at trying to model something that has occurred to a system, modeling it after it has occurred.
Right.
Knowing before and knowing after, and then figuring out what has happened. But the system is being interfered interfered with by, not mathematically, but physically and mechanically, interfered
Right.
with all through some process.
Right, that you don't understand completely. And so what we have, I mean, the idea is that you usually, after you do lots of these experiments, if you give a hormone therapy to a patient, you take a sample out of them before, you analyze the sample, you look at all the cells, and then you take a sample out of them afterwards. And you want to know what happened between, but you can't match cells up because they're completely different cells. And you want to figure out how did that distribution of cells change with this treatment. But the cells you're looking at are completely different cells than you had before, and so you sort of have to be able to generalize. This is what they looked like before, this is what they look like after, and this is the analysis that sort of links those together. And so to do that, we have these sort of synthetic analyses, which are just ones I've arbitrarily come up with. Shearing is actually for material science or mechanical engineering, useful. But the stretching and swirling are just to show the other kind of transforms that you have, to apply them to systems. And so what we see for this nearest neighbor distance is that the distance changes. So we have 0.8, 1, 1.2. That matches quite well what we expected. And the orientations don't really change at all. We wouldn't have expected the orientations to change. All of them, the distribution are exactly the same as before. This orientation is anyways not meaningful because it's a perfect grid, and so it doesn't really tell us anything about the system. So now if we look at something like shear, this then gets more interesting. And so this is a completely unsheared system. This is a system at 0.5 and 2. And so what would you expect to happen in shearing with nearest neighbor and angles?
One direction doesn't change, but say along the x-axis, it's being sheared along.
Yeah.
It doesn't change, but the nearest neighbor along the other axis will change, or it will change its angle.
Yeah. So actually, the nearest neighbor distance doesn't change at all, because as we've seen from this, that this y is exactly as it is before. There's nothing that's being changed about y. The only thing that's being changed is x.
Except that if you shear enough, then the actual point that's the nearest neighbor might change. It might be get 2 points. You lose the initial 2 points were near to each other. They move, and now those 2 points are
Right.
perhaps nearer towards something else.
Right. So that's what happens. So in 0, we have sort of the initial system as we expected at 0.5, where we've shifted it sort of halfway between these 2 points. We see that all of the orientations are now at 0 and 180, or 90 and 270, however that works. And when we get to 2, we've then sheared it enough that the point that it's overlapping with is now the next point in the system, and so it's back to being kind of normally distributed. And so what we see for the distributions here is that as you sort of start to shear, these angles, then the distribution of the angles becomes more meaningful because it's no longer equally distant to all 4 directions. It's only equally distant to the ones in this plane once you've started to shear that a little bit. Once you've sheared it too much or a lot, then it's back to its kind of original state where you don't see that anymore. And the distances are exactly the same. So there's no change in the distances because we didn't change that axis at all. Cool. So here we see the orientation goes from being sort of evenly distributed to distributed equally in every direction, to being distributed just at minus 90 and 90.